Hi guys, in this section we're going to give a little introduction to counting and probability. This chapter is a pretty fun chapter in my opinion. So in this first section we're going to begin with very simple stuff. Let's define sample space, events, and we'll focus on one rule which is the equal likely events probability rule. And at the end we'll learn how to count elements of list, sublist, and one-dimensional arrays. The book starts with this question like tossing two coins. Consider the number of heads from these two coins. Obviously, you could have no head. They're all both are tails. Or you could have one head. One head is one head and the other toss is a tail. Or you could have both heads. So in other words, we could have these three possible outcomes. Out of the two tosses, actually out of this tossing of two coins, you may have 0 head, 1 head, or 2 heads. So the question is, what's the probability of 0 head and 1 head or 2 heads when you toss toss two coins? You may think that they're equally likely, like 1/3 chance of having 0 head, 1/3 chance of getting 1 head, and 1/3 chance of getting 2 heads. Actually, this is not true. If you are able to do experiments like tossing two coins many times, okay, each time you record the how many heads that you have, and then you tally, say suppose you repeat this process 1,000 times, and you tally the results, how many times you get 0 head, how many times you get 1 head, how many times you get 2 heads. It turns out this is about 1/4 chance, this is about 1/2, this is actually 1/4. They're not equally likely. So therefore, being able to correctly count the results is actually pretty essential. Now we are going to begin with defining a few terms. We say a process is random. That means when this process takes place, one outcome from some set of outcomes is sure to occur, but it is impossible to predict with certainty which outcome that will occur. For instance, tossing a coin is a random process. Say tossing a coin, okay? Because when you toss a coin, you know for sure either head or tail will occur. This is for sure. However, before you toss it, it's impossible for you to predict with certainty whether you get a head or get a tail. So you don't know what will occur. However, you certain one of those will occur, right? So therefore, tossing a coin is a random process. And the probability theory studies probabilities or find probabilities for random process. Now what is a sample space? Sample space is just basically collection of all the possible outcomes of a random process. For instance, if you consider tossing a coin just once, so you know for sure the outcome is either a head or a tail. So the collection of all the possible outcomes, in this case, the sample space, usually we use a capital S to represent the sample space, is a collection of the possible outcomes. So I'll use a set notation. This is a sample space. An event is a subset of a sample space. In this case, getting a head is an event because it's a subset of the sample space. Getting a tail is another event. Getting a head or tail, so when I say getting a head or a tail, getting a head or a tail, this also is one event. This event is just not a simple event, it's a complex event because this event contains getting a head or tail, right, which is still a subset of the sample space. So this is still one event. So we have seen a few examples of events. Now, this is the first rule, very intuitive. The process of deriving this is skipped, so we'll take it as a fact, as a principle. Equally likely probability formula. So here it says if S is a finite sample space in which all outcomes are equally likely, so this is a keyword. So this result only applies when you have equal likely occurring event. And E is an event in S. Then the probability of event E occurring, denoted by P of E, can be calculated by P of E is number of outcomes in the event E divided by number of outcomes in the sample space. Okay, so the book provides two examples. I would encourage you to read those two examples. They're pretty intuitive, so I'm going to skip those two examples in this video. I would like to do a few other exercises so that you have different examples to look at. So now go back to tossing two balanced coins, right? So we started with that and we talked about those probabilities. Now let's really apply this new rule to find it. So tossing two balanced coins, and the sample space is, the only possibility when you toss two coins, you can either get head or head, right? So here when I write the first coin is a head, second coin is also a head, both heads. Or you can get the first coin is a head, the second coin is a tail, or the first coin is a tail, the second coin is a head, or both tails. So therefore you see that we have a sample space, the sample space, there are 4 outcomes in the sample space. Now what is the probability that, let's look at this event number, the first event. This event says at least one head is obtained. Now what are the outcomes contained in this event? So let's check. At least one head, right? So this certainly there are 2 heads, which certainly is true, at least one head. So this is 1. And there's one head here, so both are the outcomes that contain at least one head. So I'm going to list them all. And this one has 0 heads, so it should not be included in this event. So therefore this event, there are 3 outcomes in this event. So therefore the probability, if I call this as event 1, okay, so therefore this is the event 1. Probability of this event 1 will be number of elements, number of outcomes in this event divided by number of outcomes in the total sample space. So in this case will be 3 out of 4 because there were 3 here, 4 here. That's how we use this rule to calculate probability. Now here we use this rule because when you toss 2 balanced coins, we assume all these are equally likely. Each one of those outcome is 1/4 chance to occur. Now let's take a look at coin A and coin B are either both heads or both tails. We see that here this outcome is both heads, both tails, right? So either or. Therefore this event contains 2 outcomes. And you can see the probability is equal to 2/4, which is simplified to 1/2. Now next example. 3 people have been exposed to a certain illness. Once exposed, a person has 50-50 chance of actually becoming ill. In other words, we are talking about equally likely chance. So therefore, this rule should apply, right? Now let's continue to read. What is the probability that exactly one of these 3 people becomes ill? And at least 2 of the people becomes ill, none of the 3 people becomes ill. So we are going to look at this different scenario. First of all, in order for us to apply this rule in the future, we don't have to use this rule. We have other ways to find this probability. But at the moment, let's try to use this rule. That means we need to find the sample space. We need to find how many outcomes in the sample space, and we need to find how many outcomes in each event. Okay. So here, let's take a look. Let's take a look at this scenario. 3 people they exposed to illness. So let's list the sample space. So it's possible they're all after the exposure, they're still healthy, right? So let me use H as healthy. So it can be they're all healthy. These 3 people. Or it could be the last one, the third people become ill, HHI, ill. And or we can say this is possible. Second one is ill, but other 2 are healthy. Or the last 2 are ill. Okay. Or we can just continue. So the first one is ill, the other 2 is healthy. And then the first one is ill, the third one is also ill, the second one is healthy. Or we have I think that's all the possibilities, okay? So I kind of change one at a time. So keep 2 the same, change 1, and then so on and so forth. So list them systematically. And actually, there's another way to list them all out, which is the tree diagram, the possibility trees. So you do that by doing this. This is the first person. First person, there were 2 possibilities, either healthy or ill, right? And the second person branch out from the previous 2 branches. So it can be healthy or could be ill. Similarly, could be healthy, could be ill. And the third person, again, just repeat this pattern, could be healthy, could be ill, could be healthy, ill. And similarly, could be healthy, could be ill, could be healthy, could be ill. I'm running out of room here. And then how do you read the sample space? You read horizontal, like row-wise, healthy, healthy, healthy. So the first outcome will be healthy, healthy, healthy. The second outcome will be healthy, healthy, ill. Healthy, healthy, ill. And the next one here will be healthy, ill, healthy, and so on and so forth. And then the next one will be healthy, ill, ill. And just quickly write this down. And this is IIH. The very last one is III. So it will be identical to that. Now, once we find, and by the way, we see that there are 8 outcomes in the sample space. Exactly one of the people becomes ill. Let's count, okay? We see this is 1, second, third possibility. So therefore, we see that 3 possible outcomes that only 1 people becomes ill, right? So therefore, it's going to be 3 out of 8. At least 2 of the people becomes ill. At least 2. That means 2 or more. Let's count that. Again. I'm using a pink color, so I'm going to erase the previous one. At least 2. That means there were 3. Certainly, it's at least 2. So at least 2, at least 2, at least 2. Actually, at least 2 is ill. I'm sorry. I thought at least 2 is healthy, so I should count that carefully. At least 2 is ill. There were 2 ill here. At least 2 is ill. At least 2 is ill, and at least 2 is ill. There were 3 ills. Therefore, this is for sure included. So therefore, it's 4 out of 8, which is 1/2. Okay. And the last one is none of the 3 people becomes ill. That means all healthy, right? All healthy. that's just only one of those is healthy or healthy. So this is 1 out of 8. All right, this is the example of some examples of applying this rule.